Okay, so in this lecture, we will be talking about the ideal gas. Now we all know what an ideal gas is, so let me just write it down. Obeys the PV equals to nRT law. Although I have to warn you that in this course, we use M instead of N because the unit of R in our thermodynamic table is kilojoule per kilogram rather than kilojoule per mole. So we will almost never use N here, we will use M only. Anyways, obeys the PV equals to mRT law at certain P plus T. An important thing to note here is certain monoatomic and diatomic gases plus some complex gases obey this law at high temperature and low pressure. So this is the basic of what an ideal gas is. Now if you remember, we also had something called the compressibility factor, denoted by Z, small z. Compressibility factor denoted by Z. So PV equals to ZRT, which implies Z equals to PV by RT. Also, Z equals to V actual by V ideal. This V ideal is obtained from that equation, the earlier one, obtained from PV equals to MRT. So this is the definition of compressibility factor. A lot of this ideal gas stuff can be gone deep into theory, but I don't want to do that. I just want to equip you with the tools to solve the type of questions that will be asked. So this is a very concise lecture. Also, if Z is closer to 1, then gas is closer to ideal behavior. Now, our question is how to find Z? And the answer to this question is the experimental values of Z have been determined and graphed for us in our thermotables. So we're going to learn how to use that graph. In fact, if I open up my thermotables here, at the very end of your booklet, okay, I don't seem to have it, but I can still show it to you. There will be a graph. Okay. This is the graph that will be there near the very end of your thermotables, right? So let us just copy it and I will explain it to you. Alright. So for using this graph, we will be able to determine the value of Z. So our compressibility factor is on the y-axis and our reduced pressure is on the x-axis. Now what is this reduced pressure? You should remember this because it is a useful quantity. Reduced pressure is given by P given upon P critical temperature. So this is also given in our thermodynamic tables book, and you will get it from table A.2. And then similarly, we have reduced temperature Tr, which is given by T given by T crit. And again, table A.2, you will get this from table A.2. And if you see carefully in this graph, the value of Tr is this. All of these corresponding lines are for a given value of Tr. Right. So now we can find Z for any gas from this graph. Why can we find it for any gas? This is due to something called the principle of corresponding states. So it's not that oxygen will have a different looking graph than this, or nitrogen will have a different looking graph. All of the gases will have the same looking graph because of the principle of corresponding states. I'm not going to explain this principle here. I have the statement written in the notes that will be in the description. You can always check it out from there, because again, this is a problem focused lecture. Right. A couple of observations about this graph. At very low pressure, when our PR is less than 1, all gases are ideal, regardless of TR. And I will show this to you using the graph also. So, if we look at around this line, this is our low pressure region. You can see that all of the TR lines start somewhere from here, right, in this region, and then they continuously diverge. But you can see in the starting, all of these lines are very close together. They're very close together, and in fact, they're very close to 1 also, which implies all of them, regardless of TR, because all of them are starting from TR, right? All of them are ideal gases. Okay. Okay. Another statement that we can make, I don't know why I have written this in pink. Give me a second. Okay, another statement that we can make is that you don't need to remember this one, but this one you should remember. At high temp, Tr greater than 2, ideal gas behavior can be assumed with good accuracy regardless of pressure, except when pressure is very much greater than 2, regardless of P, except if PR much greater than 1. Remember, 1, not 2. Again, this is something you can keep in your mind, but you don't necessarily have to remember it. And this next one you should remember. Deviation from ideal gas behavior is greatest when pressure and temperature are equivalent to the critical pressure and the critical temperature, or PR and TR equals to 1. They are both equal to 1. Right. So having learnt all this, In the next lecture, what we will do is we will solve one or two questions using this table, and we will also take a look at some of the equations of state.